Thank you very much. Thank you very much, Constantine, for both inviting me and for the introduction earlier. And thank you, Andy, for leading in some of the context for the talk I'm about to deliver now. So we've been working on a QM in QM embedding interface for FHI-aims, which works as an external wrapper for a number of years now. And we're very happy to show you some of its capabilities and how it can help you run simulations, hopefully faster. So as Andy alluded to, higher accuracy methods such as couple cluster and MP2 suffer from quite poor scaling with respect to system size. But sometimes there are observables such as transition state energies or certain transport properties which are not accurately represented with pure PBE alone. And although DFT serves as a good compromise between the two, it doesn't always get us to the answer that we want. And this is where multiscale embedding helps us out sometimes. Now, some of the physical motivation for how we can implement embedding comes from this comes from the nearsightedness principle of electronic structure and electronic matter. So this effectively states that we can have a perturbation of the background potential that a density resides in. And as the density is further and further away from the initial site of perturbation, its effect on the density or the perturbation it'll have on the density will approach zero. And this effectively goes down to the fact that the density will only be affected by potentials in a given vicinity. So this means that we can describe a certain part of our system with a different level of theory without describing a part of our system that we're particularly interested in. So Andy has just gone over what is embedding, and he's gone over what a subtractive scheme is as well, where you essentially just describe a small part of your system with a high level of theory and then subtract out the corresponding subsystem described with a lower level and less expensive level of theory. So you are describing the boundary between the high level and the low level of theory with the interaction terms of the lower level of theory. And this, Andy was discussing QM-MM, but we should probably go over why you would want to go to a scheme that uses quantum mechanical and quantum mechanical embedding over the classical term. And part of this comes down to a lot of the parameterization that you have to do to get some of these QM-MM models to work properly. So a lot of the errors that come from QM-MM come down to the interface region between your QM and MM regions. And this is largely an artifact of the fact that you're describing two regions of two systems in close contact with each other with fundamentally different physics. And to get accurate results, you sometimes have to parameterize the force field to a reasonable extent to get an accurate energy. And we can see this, in the number of atoms that you have to introduce for a QM region. So sometimes you have to include hundreds of atoms to get an accurate energy, and sometimes that's not. Sometimes that's not feasible for the more unfavorably scaling methods. So we move on to what we've introduced in FHI-aims, which is projection-based embedding. So like QM-MM embedding, where you describe a small part of your system with a higher level of theory, you're now describing the wider environment with another quantum mechanical method. So for example, for DFT and DFT embedding, you describe the whole system, both of your super system with a method 2, as you can see here, and you can subtract out the corresponding region of the active region with the lower level method, and then add in the high level contributions of method 1 described with the density matrix that corresponds, which is being optimized in the embedding potential. And this also can be applied for wave function in DFT embedding as well. So this is where you subtract out the low level of theory described at the DFT level of theory, and then add in an energy contribution from a wave function method such as RPA, or MP2. So how does this work in practice? So projection-based embedding starts off with the density matrix. So you start with the supermolecular density matrix, which is described through the molecular orbital coefficients from solving the Cohen-Sham equations. And to get the density of your two subsystems, you localize the molecular orbitals and partition the density into two disjoint subsystems A and B. And this is generally achieved using a unitary transformation matrix or some form of transformation method, such as either a singular value decomposition, or you can use a more of an old school method like Pipek-Mézet or Edmondson-Rudenberg to move from the canonical Cohen-Sham wave functions to localized wave functions, which you can then select based on where they lie in your system and whether they're centered on the region of interest or whether they're concentrated in your environment. And projection-based, because it's called projection-based embedding, you can quite rightly surmise there's going to be some form of projection involved. And the way this is accomplished is using a level shift operator, as shown here. And effectively, what this does is it takes the density associated with region B. This should be superscript B, apologies. And shifts the molecular orbitals associated with subsystem B to a region to the higher part of the energy spectrum. So this mu value here is generally 10 to the 6 high Hartree, so it moves all of the molecular orbitals associated with subsystem B far, far above the virtual orbital space you would find in a typical calculation. So in effect, when you perform the Cohen-Sham, when you use your embedded, when you solve your embedded Cohen-Sham equation, you will never optimize into that region. So you maintain perfect orthogonality between subsystem A and subsystem B. So this all comes together in the projection-based embedding scheme where you construct the embedded Fock matrix. And you use this to find density matrix, subject to the high level of theory. So you can either use the same level of theory, a GGA, or you can use a hybrid level of theory. And you construct the embedding potential as such. You take your supersystem Fock matrix, you subtract out the lower level theory contributions, and you add back in the Fock matrix, which corresponds to the high level of theory density. And once you've put all of these terms together, you can then solve the standard Cohen-Sham eigenvalue problem with this new density, with this new embedded Fock matrix to obtain the density matrix of the high-level embedded subsystem, and then just bring all your energy terms back together, and then you have your DFT and DFT, or wave function and wave function energy. So this is all well and good, but as you've probably surmised, you have to perform 3 different calculations, and in as many electronic structure codes generally have a monolithic design as such, where you can just treat them as a box where you put in input and it performs a self-consistent field calculation and it calculates the total energy. To have QM and QM in many electronic structure codes, you have to put a lot of the machinery of embedding into the software, and you also need a high-level wrapper that calculates the different subsystem energies. So, for example, you would need a routine that takes in this energy and then calculates this energy and the density matrix, partitions it, and then calculates the subsystem energy. And as you can imagine, this becomes very complicated in fairly large electron structure codes, where many variables are defined at the beginning of the calculation from the input file, and this is a fairly unsafe way of coding if you're essentially changing not only your level of theory that you're calculating, but also which part of the geometry that you're interested in, and different different matrix extents that you would have to allocate and reallocate and deallocate. So this is why we went for something which is more modular. So instead, what we've done is we've gone for a Pythonic style wrapper where we define our inputs using something like ASE, and then we use an interface or a C-based interface, which I'll come into later, to call FHI-aims as a library. So we can then calculate the supermolecular system. We can then perform the partitioning in the Pythonic wrapper, and we can then call the subsystem calculation at the low level of theory, and then we can calculate the embedding and projection matrices, and then calculate the final high-level energy. And what we hope this does is create something which is a little more reusable and can be extended to other codes. And not only this, we can apply this to other forms of QM and QM embedding. So Dando Chavez, who I've worked with on EmbASI, has also implemented a frozen density embedding theory implementation that works with AIMS as well. So other forms of embedding are implementable and they're available in EmbASI. And the glue that holds all of this together is the ASI C-based API. So what this does is it allows you to take the data structures I was talking about earlier, so the density matrices, the Hamiltonians, the Fock matrices, and communicate them back to the wrapper using C pointers. And the advantage of this approach is it allows us to place in information and take out information from FHI-aims without resorting to a file I/O mechanism. So we can just keep everything in memory. We can perform copy operations if we need to, or we can just use the C-based pointers without deallocating them in the code. So this saves us a little bit of trouble in the sense that we're not shuttling information to the disk, which is hopefully a little faster. So overall, the EmbASI workflow looks a little like this. So you initialize your inputs and define your ASI callbacks. You gather the density matrix of the total system, and this involves calculating the low-level reference Hamiltonian. You take back your electrostatic embedding for the whole system, and then you localize, divide your density matrix into subsystems A and B, calculate your embedding potential by calling the low level of theory onto the active subsystem, and take the electrostatic matrix back from there. And then you calculate the projection matrix from the environment density matrix, and then use all of these terms together to calculate the final density calculated at the high level of theory to give you your total energy. So now that we've explained all this, we can now move on to some of the test cases. So a lot of the test cases that we used are simple systems, but what I'll also demonstrate is some of the scaling to more complicated and slightly more sophisticated systems. So let's start off with the pentanol dimer. So this is embedding a pentanol dimer with a small active region of the two OH moieties, and we are measuring the dissociation curve as you move these two pentanol dimers further away from one another. And generally what you want to do is you want to take the normal PBE calculation, which is calculated for the supermolecule, and then compare this for PBE and PBE. And what this does is it gives you an absolute baseline. Does this work? And if there is an error at this level with the given orthogonality constraints that you put into the system, you can pretty much guarantee that there's been some kind of bug introduced into it. But luckily here we have PBE and PBE embedding working. And then something a bit more interesting, where you have PBE naught in PBE embedding. We see a small error of about 0.2, 0.3 kilojoules per mole, but this is well within accepted bounds of accuracy, I would argue. But we run into a little bit of trouble when we start running RPA in PBE embedding. So what we have here is RPA at PBE and an error of about 10 kilojoules, 9 kilojoules per mole at the closer extents. And this, although it decreases over distance, at the equilibrium distance between the two PB pentanol molecules, we end up with an error of about 3 kilojoules per mole. But we can ameliorate this error by increasing the size of our active region. So what we have here is the result I just showed you with a little bit of a speed up, but the speed up is pointless in this case because we're essentially far above reasonable bounds of accuracy. But as we increase the number of atoms that we include in our active region, you also decrease this error for RPA. And although this moderates the speed up slightly that you get for RPA, we can keep doing this. And we roughly get to a reasonable level of accuracy at around the second or third nearest neighbor from the oxygen moiety. And you get some moderate speed ups for free with RPA. This is not necessarily the case with GGAs and hybrid functionals, mostly because you're still performing integrations across those basis sites in the original implementation of QM and QM embedding. Whereas with RPA, when you decrease the size of the active region, you're increasing the size of the virtual orbital subspace at the expense of the occupied subspace. And given that it scales n to the 4, based on with two of the n terms being the virtual and the other one being the occupied, you end up with a more favorable scaling the smaller you make your active region. So we get this speed up for free with RPA, which is very nice. So as I just alluded to, when we include, for the form of QM and QM and projection-based embedding that I just presented, all of the basis functions are included in the high-level calculation and all of your subsystem calculations. Now, we know from the nearsightedness principle, and we know that some of the charge contributions to the active subsystem are not going to be all that important. So we know there's very little charge from the active region, especially if we localize our charges that reside within the environment subsystem. So what we have here is the ghost atoms that you would see ordinarily in a calculation. But what we can do is we can use a form of basis truncation which removes ghost atoms from the environment that we're not interested in. So in this case, we use a Mulliken-based threshold that essentially tells you, given a charge criteria tau, whether we're interested in a ghost atom. And if it doesn't contribute a significant amount to the inner active region, then we just exclude that basis center and we remove those basis functions. So let's go with the example that I've just shown. So this is an organic acid dimer. And what we have here is effectively what happens when we decrease the truncation threshold, which is measured in standard charge units. Bushy-eyed and eager among you may not, as we say, chemical accuracy here. I'm not too happy with that label, to be honest. Just treat it, because we're measuring this relative to the full PBE calculation or the full PBE naught calculation, but just treat it as a rough threshold of about 4 kilojoules per mole accuracy. And what we see is, as we decrease the threshold, make it tighter, the error in the dissociation energy between these two dimers also decreases. So we go from 10 to the 4 kilojoules per mole, which is a crazy level of error. And as we decrease the threshold, we end up with something a bit more reasonable. So about below that 4 or 2 kilojoule per mole threshold. And what we see here for PBE are some moderate speedups, but nothing that's going to break the bank, nothing that you would incur this level of inaccuracy for. But as you increase the number of so as we go to PBE, we see that the scaling, as we increase the truncation threshold and we decrease the number of basis functions that we include in the high-level calculation, we see much more favorable scaling. So our calculation, so the high-level calculation in this case is 3 times faster than the untruncated form over here. And as we move to RPA, this is where we start getting the most dividends from the speed up. So we take, so when we go to the level of truncation that we're interested in, we can get up to 15 times speed up for the high level calculation. And as RPA is probably going to take the lion's share of calculation time for systems of this size, we would probably consider this as reducing the big headline number in terms of wall time, while also keeping within a reasonable level of accuracy for the dissociation energy. So we've gone through these toy systems. That's all great. That's all well and good, but they're not really where the strengths of QMMM are the most obvious. So what I want to show you in the last 10 minutes of the talk is the advances we've made in introducing infrastructure to make EmbASI a bit more scalable. And this includes MPI support and Scalapack support for some of the linear algebra machinery that operates within EmbASI. And to do this, we're going to take what Andy was showing before, some of these zeolitic systems. So in this case, we've got a hydrogen-capped zeolite of about 686 atoms. And we can demonstrate that these calculations can run fairly well. And the reaction, and the observable that we're going to measure everything against, is the reaction energy of this reaction here. So this is methanol to DME. So this is the bringing together of two methanol molecules on this zeolitic acid site to form DME, which is a key initiation reaction within the methanol to olefin process. So first, let's just demonstrate that we're reasonably scaling in terms of memory with these large matrices within the Pythonic wrapper. And we can show that we're indeed accomplishing this. So as we take this 686 atom cluster, and as we increase the number of nodes that we assign to the calculation, you get what you expect. You get a decrease in the amount of overall memory usage per core. That's nothing fancy, but it just shows that we can at least scale in terms of memory, and timing scaling also works reasonably well for the linear algebra operations that we perform in EmbASI. And also, we hope we have a performant way of mapping between the truncated and full supramolecular basis representations of the density matrix and the Hamiltonian. And finally, just to show a more practical system, we have a PBE naught in PBE embedding calculation for our 686 atom cluster. This is a 3 nearest neighbor active region. So we include the T site in the center, and then 3 nearest neighbors around the central site. And what we have is something that we have to bear in mind. So when we deal with embedding calculations, we have to deal with not just the overheads associated with truncation, but also the overheads involved with embedding. So when you have to converge a number of things when you're running these calculations. And although the reaction energy, as defined here, we're at about 4 kilojoules per mole, which is not a great level of accuracy. So you would probably want to increase the size of your QM region just a little bit. But we find that our activation energies are somewhat performant below this 2 kilojoule per mole threshold. I would consider fine and happy. And the other thing, we have our error associated with truncation. So what we take is, we take this large cluster, we cut out an active region, and then we truncate the basis for a PBE naught and PBE calculation. And for a threshold of 10 to the minus 4, we're getting essentially at negligible levels of error. And on top of this, we get a relatively good speed up out of 10 to the minus out of this 10 to the minus 4 threshold versus the full PBE naught calculation for the total energy. So you can see here, we get about between a 4 to 5 times speed up compared to the full PBE naught calculation for the large zeolitic cluster. So that demonstrates everything that we've been doing with EmbASI recently. We have some extra development work going on, but what I'm hoping we've demonstrated is that EmbASI can reliably and in a user-friendly way execute QM and QM embedding calculations. And not only this, we can extend the types of systems that we can run RPA calculations for. So for RPA and PBE embedding, we can run those calculations with a relatively minor impact on accuracy. And we've also demonstrated that the framework scales to larger system sizes as well. So atom counts of 686 plus 1,000 atoms. We've not run anything much beyond that because it's frankly not that useful for the systems that we're thinking of. But if you've got a use case for us to really stress out the framework, please let us know. And for future work in development, so spin polarization support, that is on the cusp of being done. That's going to be merged soon. And other work associated with absolute truncation. So not using this parameterized charge-based metric, but using a freeze and thaw style algorithm to optimize the two subsystems separately and then calculate the embedding potential from there. And that should be very, very favorable and very good for our wave function calculations. And then other things in the works. So there's probably more than I can fit on this slide, but as we've also have an electrostatic embedding interface through ChemShell in development in conjunction with a project student we had in the summer. And we're also working and tackling the big beast of analytical nuclear gradients for these types of systems, which I'm not looking forward to, but that's just life. So thank you very much. I'd like to thank Andrew Logsdale, my supervisor, Pavel Stashenko for his contributions to ASI and Scalapack for Pi and all of the other 4 Pis that he's worked on. I'd also like to thank Oscar Van Buren, and also not on this slide, but I do want to thank Danjo Chavez for helping me work on some elements of the EmbASI infrastructure, which have been, which hopefully we'll see more use out of EmbASI soon. So thank you very much. As I said, we'll probably talk about the tutorial and hands-on session led by Oscar, but I'll also be there briefly just to talk about some of the tutorialized elements of EmbASI as well. Thank you very much.
Thank you, Gabriel, for a very nice talk. And then once again, I would open the talk to questions from the audience. So please feel free to ask a question for Gabriel. We'll also check some of the other channels in case we have some there.
Maybe I can ask one while people are thinking. So for these, for the basis convergence threshold, do you always have to converge it, or can there be some kind of, I don't know, sensible parameter to choose? And how much is it like affected by the basis set size, the QM methods, and the system?
So in my experience, I find 10 to the minus 3, between 10 to the minus 3, 10 to the minus 4 to be a reasonable compromise. But I think it somewhat depends on the size of your system. I've only really tested between PBE NOR and PBE for the truncation threshold, and you seem to get fairly similar behavior between the two. So you converge to a similar place. In fact, we can just show for the truncation thresholds the effect of functional. In terms of basis, I don't believe there is too much of a change, but I probably only checked between the basis thresholds, the NAO 3Z types of basis to the 5Z type basis, and I don't really think there's that much of an effect for the truncation thresholds there either. I think because it's atomic base, I think if you had something which filtered in terms of basis function, you probably would have a bit more sensitivity there, but I think having the atomic base threshold does somewhat ameliorate some of the issues of that.
Okay, thank you.
Thank you, Gabriel and James. There's one question again from Katharina in the chat. In the embedding method you use, you can treat charge transfer from one fragment to the other, right? Does the localization have to be possible through occupied orbitals only?
So there are some localization schemes that deal in the virtual space. They are a little trickier and they converge. They take a little longer to converge, but they do appear to work anyway for simple test systems. For this system, I don't believe there is charge transfer allowed between the two subsystems. So when you localize, you do define the charge that resides on each subsystem, and then you kind of fix the charge, allowable charge for each subsystem. That comes, and you're informed how much charge each subsystems will have just through the localization algorithm. I'm not sure whether that fully answers the question, but I think there are, if you wanted to have more sophisticated like charge transfer between the two systems, you would probably need to look at something like DFET or something of that nature.
Thank you, Gabriel. Katrina, hopefully that answers the question. Otherwise, feel free to ask a follow-up once again. Andy, I think, wants to maybe chime in.
Yeah. I want to ask a question on top of this, right? So, because it's quite a nice question because it takes you into the space of things like excited state chemistry. Do you have a feel, Gabriel, of the cost to do the localization in the virtual space?
So
relative to the cost of doing in occupied space. Sorry.
So I think it depends on the extent of the virtual space. Because I believe the localization algorithm that we have implemented in FHI-aims that can deal with the virtual space is on the, I think it scales n to the cubed with the number of states that are included in the calculation. So it will probably get quite expensive, probably on the order of the diagonalization, but these are, again, just these are n state by n state arrays rather than n basis by n basis arrays, so they're not as expensive or as dramatic. But I believe there are excited state implementations, including TD, DFT, and GW-based implementations of projection-based embedding that don't require localization across virtual space as well. So I think they just use the ground state truth of the supermolecular system, localize, and then just perform the excited state calculation on that subsystem in the presence of the embedding environment, if that makes sense.
That helps. Thank you.
There's also, I guess, a comment from Danjo concerning the question. He mentions explicit charge transfer needs DFET, so density function embedding theory, through the Wu-Yang functional. So I guess that's more of a comment related to the question. There's a follow-up from Katharina. So she says, the question comes from the use case for non-insulators. So in principle, it sounds as if the method were applicable, but only if one is sure that the high-level cluster includes all shielding charges in the conductor that may occur.
Yes. So I would probably be a little skeptical about running this type of framework with anything without a significant band gap, because I don't believe the localization will behave in a nice way. So you won't be able to construct a decently localized embedding potential that encompasses the entire environment. You'll end up with like little bits of mixing between the two in a continuous spectrum of states that that extend across your defined environment and active region. So perhaps there is some way to get it to working. I've not really tried with non-insulators, but I think there are schemes which are probably a little more performant than projection-based embedding for that particular problem set.
maybe if I can just come in for very quickly on this. Sorry, James, just jump in front of you. Of course, Gabriel, the solution here that you're working on is the frozen density embedding, which you haven't covered today. Danjo.
Yes. So the frozen density embedding, and also Danjo's working on the DMET implementation as well, which operates within FHI-aims, and that's probably a bit more performant for non-insulators and systems with small band gaps.
Okay, thank you all. Katarina also says thank you. James, is that a follow-up or is this a new question?
No, follow-up. So kind of on this point on the how to partition the state or the orbitals and occupied and virtual states. So would it also be possible to use something like a fragment molecular orbital approach? I don't know if you're familiar with this, but there is some code in FHI-aims which implements this like fragment molecular orbital method.
There is, and I think in principle that should be possible. I think the framework would allow it. I think it's just a matter of I think it would just be a matter of properly defining the subsystems and then mediating the interactions between each of the subsystems, because there are as in the frozen density embedding, a way of transferring the external potential to and from FHI-aims through file I/O, but we need to implement the import mechanism for the Cartesian space embedding potential to have this basically on the same kind of framework footing as a projection-based embedding. But it's still possible with the file I/O and using EmbASI as kind of a wrapper just for executing calculations and letting it know where different pieces of the embedding potential are within your file system.
Okay, thank you.
Yeah, I've just allowed Danjo to speak, who raised his hand. So maybe you want to add a comment also.
Hello, can you hear me?
Yes.
So and just want to jump in with what Andy said. So the FDET actually works with no band gaps for metals. I did test it with a cluster on a cluster system for aluminum, and that works at least in that small test case. But the status of the frozen density embedding in AIMS currently is limited to cluster, no periodic embedding, basically.